My name is Nathan Furiotti. For this presentation, we will be discussing a toolbox for assessing the impacts of cyber physical attacks on water distribution systems. This was a paper, a toolbox for assessing the impacts of cyber physical attacks on water distribution systems, and it's also an actual tool set that the authors of the paper created. The toolset is available on GitHub, and that link will be shared at the end of the presentation. The paper, as I've named now, was published in 2019, and it was done so by a group of researchers from across the globe, both in Singapore and in Israel. And the framework that they released allows for modeling water distribution systems not only in a physical way, but also to understand the software and how that models into the physical system. Their software is called EPANET CPA, and it's based around a core toolset called EPANET. Not sure exactly how folks like to pronounce it, but it is a open source piece of software itself, and it was actually developed by the EPA, the Environmental Protection Agency in the US. So we'll be going over what open source software is related to EPANET, why the tool set that was developed is important. We'll go over the tool set itself, EPANET CPA, which is the tool set the authors wrote. We'll go over its capabilities and what we can analyze with it, how we can define different scenarios with it, and the use cases that it might help researchers solve. The EPANET software that the EPANET CPA software our researchers wrote is based on was, as I mentioned, created by the Environmental Protection Agency. And it's used to simulate water systems for researchers to understand how different components in the water system might interact with each other and simulate their flow states over a set of time. So these models would be used to understand large systems, water systems across the United States, and can help for planning out these systems and understanding how a system might affect customers of the system when it's processing water in different ways. It can also help researchers understand the chemistries of what's going on inside the pipes, for example, in the systems or inside other units in the system. So on the right here, this visualization shows kind of the beginning state of a simulation, and I think we can play this out here. It will model out how the system is filling up with water as different events occur. And we've included a link to EPA's visualizer for this. So the EPANET software is itself an open framework that allows easy expansion and collaboration. So this is not something new that the researchers are trying to, create this whole new ecosystem. This ecosystem already exists. So the ecosystem, there's a tool set for using R programming language with it. That is called EPANET 2 Toolkit. And it also allows for some more advanced simulations of water. There's a EPANET MATLAB, and that's a plugin that just allows for MATLAB programming with the EPANet framework. And there's a water network tool for resilience, which is a Python plugin, which allows for building out these visualizations with Python. So EPANet CPA, which is the software introduced with this paper, allows for our cyber components to be plugged into these physical water distribution systems. All of the software previously mentioned, while nice to have as different options for EPANet, they don't allow for understanding how cyber and software components, which is a large aspect of water distribution systems, how they can be modeled. So why is being able to model the cyber components of a water distribution system important? Well, this is an increasing threat to water systems across the globe. Just recently in the news, it felt just so timely, I needed to include it, that we've had an attack on the San Francisco Bay Area water and a water treatment facility there. And in February 2021, there was an attack on a Florida water supply system where hackers remotely accessed the computer network in the system and were able to increase the amount of lie in the system to unhealthy levels by a factor of many times more than it should be. So this hack was actually recognized when employees saw a mouse cursor moving on the screen and the cursor was beginning to delete files. So there are many different ways that hackers are affecting these systems, and apparently taking advantage of remote access is one of them. So EPANet CPA allows us to model how these hackers might intrude or cause destruction on our water distribution systems. It allows us to model out all the different components in a cyber-physical water distribution system, including the sensors of the system, hydraulics valves, and the central operating system that's orchestrating all of the physical nodes in the network. All of the modeled components can be attack vectors. So it's important that we have these tool sets to be able to study how these attacks might manifest themselves. So EPANet CPA will be a good platform to be able to develop out a framework of better understanding, essentially, on these attacks. The two main components of a cyber portion of the system that can be modeled are PLCs, which are programmable logic controllers, and SCADAs, which are supervisory control and data acquisitions. I'm going to describe what both of these mean here coming up. So PLCs use picked up in the 70s, and it's a process that continues to grow. It allows for the automation of industrial systems so that we don't have to have someone manually controlling each of the different systems in the factory or in the industrial system. Instead, we can use these automatic sensors and actuators to control the system electronically. And the SCADA is the software system that ties all of the sensors and actuators together. It will react to the sensors and what is happening with the sensors, and it supervises the state of the system. And it will also be used to operate the actuators in the system and keep everything working together. And an interesting part of the SCADAs is that they monitor a very large geographic area, which is unique to them. However, if we don't securely utilize these SCADA systems, they are extremely vulnerable to being overtaken and can lead to destructive circumstances that might greatly impact your system, since it is so central to the entire system. So how does EPA Net CPA come in? It will create a graph between the two layers of the PLC and the SCADA. And with that, we can monitor different impacts on our water distribution system, such as what is the demand impacts of an attack, or what are the pressure or physical impacts of an attack. So the demand-driven analysis gives researchers to understand what will happen to our customers. How will this play out? How will this attack play out as far as how will our customers be impacted, and what is the timing of that? And a pressure-driven analysis will allow us to understand the different components inside of the system and what are their actual pressures and how the physical manifestations of the cyber attack are playing out in a timeline. So we're able to construct these simulated attacks pretty simply. It is designed to just be a few commands to get up and running with a EPA Net scenario. So we will feed the simulation a standardized EPA Net format, which is exactly like we would find from EPA.gov's EPA Net tool. And this is just a long list of, it's basically a CSV file that is just comma delimited with all of the different nodes in the water system and how they should connect together. And then the second command to get things running is literally just simulation.run. And our third command will save the results of the simulation and output those so that they can be used for researchers in different ways further down the line. So for defining our simulation and the parts that are unique to EPA Net CPA, we will create a scenario file. And in that scenario file, there will be different sections. And the CyberNode block section is where we can define all of our different PLCs and the SCADA, if there is one. So with this section, it's very straightforward. It would just be a block, as this code shows, where we would define a name for the node, a sensor, and an actuator that we can point the sensors and actuators towards a name. Just by defining out this list, we'll be able to, so the EPA Net CPA will be able to know which nodes should be part of the simulated attack. And then we also need to define a cyberlink section for our simulation. So we would define a source and a destination and the sensors that are relevant to the link. So you can see here, we're defining just like those names we had on the previous slide in our cyber nodes block. We'll reuse those names and we'll tie them together now with a source and a destination. And we can see how this would allow us to build our network up and allow our SCADA to be represented as the central command center, essentially, for the water distribution network that's simulated. So for defining our attack, we are able to make use of this cyber attacks block, and we're going to be able to define 5 different arguments that can play out in our attack. So the types of attack to be completed, there's a few different attack types that we can choose from. And in this scenario, we're using the communication attack type. So we're also able to place a target for the attack. And we'll be doing this to reproduce a denial of service style attack between a connection, just overwhelming that communication. Additionally, we can place different start conditions and end conditions on the attack. This will allow us to trigger the attack at a specific moment in the water distribution life cycle that's being modeled. And it can also allow us to build up some different types of logic bombs, essentially, where we can place the code to only be activated on certain conditions being met appropriately. Same for the end condition. If we want to have an end condition, we can place it so that it happens on a logical basis. And finally, we place the adversary action as what type of action the adversary is taking on the target. And like I said, in this instance, it's a denial of service attack. So there are different types of attacks possible. Those can be defined just as shown in the cyber attack section that we're looking at on the previous slide and this slide. The attacks allowed are an attack on a sensor, an attack on an actuator, an attack on control, and attack on communication. So this block defined here shows the control logic of some pumps being attacked by turning them on and off at the different set times. So we can see time 30 and time 35. We're seeing these pumps being controlled and being shut on and off in a way that simulates an attack. So there are different possible ways to trigger these attacks, as I mentioned. So we can use a time-delayed attack, logic bombs based on different sensor levels or the states of valves or pumps. We can even use attacks to trigger other attacks and combine attacks together so that they're working simultaneously in a way that a real attacker very well might do to take over different parts of the system to better mask the attack that is happening and perhaps induce further confusion or effectiveness of the attack. So in our simulated attack, we will get an output that will allow us to visualize how the attack played out. In this scenario, this attack shows 3 different things happening. So in the first graph at the top, we see what the normal water distribution tank level might look like in this system. And we're able to see how this changes after an attack. So this DOS attack is hitting the PLC1 node, and that is bringing the node offline, which we're seeing by the dashed line, which is the sensor for it. And then we're seeing that the attack is being masked in the final slide C. So we see that the dark line, although it is going up, We can see that in the third slide versus the second slide, the SCADA is being read not with the actual values of the tank level. Instead, it's being forced to, via a replay attack, to show a similar pattern to what would be expected of the water tank levels in a normal, undisturbed scenario. Additionally, along with these graphs, the program will output some CSV files, two CSV files, which will have the time series data of the simulation and the physical data of the system. And that's really helpful for allowing researchers to continue their understanding of the data and perhaps apply further methods for understanding. So the use cases of the EPA-NET CPA is that we can now create data sets of our water distribution systems, and we can mock out all of these different scenarios in which we might be attacked. And by doing this, we should be able to create much more resistant systems and learn in a way that allows us to build better water networks. We're also able to take this data from the CSVs that are outputted, and perhaps we can start to apply learning algorithms to the data that's given back, or take the data and just continue the analysis for building more secure systems. So in summary, this EPA-NET CPA toolset is a fantastic open source contribution to cyber-physical water system research, because it's allowing researchers to get their hands on this tool to further their understanding, and it's also allowing anyone, since it's open source, to contribute to it or to use it. The authors mentioned that they want to encourage user feedback, and that's part of the reason I think that the platform is chosen to be launched in an open source way. And it's also consistent with other research tools in the EPA-NET ecosystem, is that seems like most of the frameworks that I saw were just open source frameworks that worked off of that system. So this provides a launching ground for taking research to the next level and expanding on what the authors have already created. So just some quick links here if anyone would like to check out the source code. The source code's all there and on GitHub, and the paper itself can be found at the link provided. And just included here other sources for understanding PLCs, SCADAs, and the recent activity of hackers for hitting water supplies just this year. Thank you for your time, and excited to take any questions on the topic. Thanks.